Am I online now?
Yes.
But I can't see the screen. Oh wow. Okay, there. I guess we can start.
Yes, please. We all know that.
Okay, I'm pleased and honored to be here today to introduce you to Adamantios Gafos. This is Abralim ao Vivo, Linguistics Online, an initiative of Abralim, Brazilian Linguistics Association, in cooperation with several international partners, among which the Comité International Permanent des Linguistes, the Associação de Linguística e Filologia de América Latina, Sociedade Argentina de Estudos Linguísticos, the Sociedade Espanhola de Linguística, the Linguistic Society of America, the Linguistics Association of Great Britain, Societas Linguística Europeia, the Australian Linguistic Society, the Association Internationale de Linguistique Appliquée, and the British Association for Applied Linguistics, to name a few. I must introduce myself. I'm Eleanor Alban. I've been around for a while, trying to integrate phonetics, phonology, phonostylistics, and I'm a retiring, not yet retired, professor at the University of Campinas in the state of São Paulo, Brazil. It's really a delight to introduce Adamantios Gafos, who is professor at the University of Potsdam, Germany, in the Department of Linguistics in the excellence area of cognitive sciences. His PhD is, in fact, in cognitive science from Johns Hopkins University, 1996, a while ago. He taught at UMass, Amherst, MIT, NYU, before moving to Germany in 2011. He's also a senior scientist at Haskins Laboratories since 2000. Well, he said that there were no highlights he wanted me to make for his talk, but I think I must introduce two. Okay, one is that his birthplace is the birthplace of Western academia, and the term academia has come from when he was born. The same birthplace of democracy. Okay, this was a long, long time ago, but Adamantios has also listed in his longer biography a number of grants he's responsible to, and unfortunately, at home, he might not be able to get funded the way he gets elsewhere. But he's a true Greek with all this heritage. Okay, so let's not wait more to give the floor to him. I'm very happy to be here. Adamantios, please go ahead give your talk.
Thank you very much, first of all, for the opportunity to speak in your series. Since Eleonora went off the beaten path, so to speak, I also would like to reciprocate here and say a few things. I believe you've taken a rather challenging situation of isolation and turned it on its head with this series of talks that a number of people are putting together, and Miguel is devoting his enormous amount of time and organizational skills to do so. So again, once more, thank you for the opportunity to speak here. Given that we and you and many others are facing unprecedented challenges these days, the fact that you're organizing this makes it even more effective and even more moving. And the organizers explained to me that part of the rationale for the series was to find ways to inspire or maintain or even bring into the field young people of diverse origins who have not been involved in the field of linguistics as much as we would have liked them to be. And I hope your series serves as an inspiration to many people and other cultures to face the challenges that we are facing these days. So with that, please let me know when I can share my screen so that I can project the slides. Okay. Presumably the slides are now projecting. Okay. Yes. Thank you for confirming that. So the work I will be presenting today is in collaboration with colleagues and recent PhD students. These names are listed here. About 100 years ago, 1925, Sapir published a paper in the very first volume of the Journal of the Linguistic Society of America. The journal is called Language, wherein, among a number of other central questions, he posed the question, what is linguistic about speech sounds? In other words, what makes certain sounds or certain acoustic events have the status of speech sounds or words as opposed to any other sounds that can be generated by a human? So Sapir is telling us that a speech sound is not merely an articulation or an acoustic image, but it's material for symbolic expression. In other words, speech sounds carry meaning and they function as a message. In what follows, we're going to concentrate on this key property of messages. A sound can serve as a message that is convey information only in the context of a set of alternatives in which it operates. Sapir called that its placement throughout his work. This notion of set of alternatives is fundamental to any communication system, and in particular to the attendant theory of such systems, Shannon's mathematical theory of communication. Shannon started his landmark paper by explaining that messages should be thought of as sequences of choices among a set of alternatives. So this is the key notion I'm going to be highlighting throughout the talk. In particular, I'm going to rely on this notion heavily, and I will argue that is fundamental, that it shows up all over the place, in production, in perception, and in phonological rules. In a historical context, I should say that similar ideas by major thinkers on symbols have appeared in the fields of physics, so in particular von Helmholtz, who was a physicist and a physiologist, who was interested in the semiotics of science. In the field of semiotics itself, Umberto Eco, one of the major thinkers of the notion of symbol, and in the field of theoretical biology, Howard Patti. So thinking of messages this way, we will explore the sound patterns in language in three very different domains. learning of words in acquisition, learning of phonological rules in the artificial grammar learning paradigm, and in part 3, the speech versus non-speech, or the plausibility of drawing a distinction between speech and non-speech, an issue which was very dear to Sapir, at least in this 1925 paper. And my aim, or the plan of the talk effectively, is to take this idea of the choice among alternatives, in particular, to take an appropriate formalization of this idea, in terms of the cardinality of the set of alternatives, how many there are, and the specificity of the set of alternatives, how distinct they are from one another, and show that it leads to simple and sometimes surprising responses to present-day debates in the above domains. The 3 domains I chose here are sort of a selection. However, I believe that they are deeply related to one another with respect to choices among the alternatives idea. However, the talk will not be about the ratio among different domains. So in a sense, you can treat the talk as effectively a set of 3 mini talks. So let me get started with part 1. This is the word learning part. I'm interested in the habituation switch paradigm, which is one of the main workhorses for language acquisition research, and in particular, word learning experiments in language acquisition research. During this paradigm, an infant or a set of infants is habituated to 2 pairs of stimuli. One pair consists of a visual stimulus, for example, this green round object that is shown on the top here. And the other stimulus is, an acoustic stimulus, which is a stream of acoustic productions of a word. In this case, the word is book, beginning with a voiced B. The other pair of stimuli is once again a pairing of a visual stimulus, shown here, and a stream of acoustic stimuli, here now beginning with a voiceless OP. And in the test phase, the infants are tested on their ability to detect a switch in the pairing. So about 30 trials of habituation phase go through. And then in the test phase, the infant is tested on a same versus a switch trial, where in the switch trial, the pairings have been inversed. So in other words, whereas the visual object that's shown with a round green circle or so is associated to the voice OP, it will be associated to the voiceless OP in the switch pairing. If the infants look longer at the switch trial as opposed to the same trial, then this is taken as support for the claim that the infants have learned the association between the acoustic stimulus and the visual stimulus. Now, this is a paradigm that has been powering a lot of insights into the field of acquisition since its adoption to the field of acquisition by Steiger and Werker. And one of the lessons that has been learned in this paradigm is that there is no robust switch effect for minimal pairs, at least for 14-month-olds. So in other words, researchers do not always get a switch effect. The switch effect is again the effect where the switch trial, you get longer looks in the switch trial than in the same trial. And this results, so the non-consistent presence of a switch effect is related to the claim that word learning is more than just discrimination. We know this because it is demonstrated that the perceptual acuity to do word learning is there in full force, because we know that the infants can discriminate between voiceless and voice stops, for example, in work by Werker and Tees, Kuhl, Jusig and Aslin. But this ability apparently is not sufficient to allow the presence of a switch effect. There is 2 factors that have been implicated in the modulation of performance in this task. One is a task effect. That's a sort of a standard factor implicated in psycholinguistic or psychology experiments. So there's something about the complexity of associating visual stimuli with acoustic stimuli that may prevent the emergence of a switch effect. The second factor, of course, is a signal-based factor. So we have a task factor and a signal-based factor. And the signal-based factor is claimed to be something about the structure of the acoustic variability or the lack thereof in the stimuli that may prevent a successful association between the visual stimulus and the acoustic stimulus. What I will do in part 1 of the talk is I will explore the extent to which we can synthesize the two. So I will begin with some basics on probability, and in particular, the fact that the probability of an event E can be interpreted as a measure of uncertainty about the non-occurrence of the event E. Suppose you believe or you have made an estimation that the probability of your event E is equal to 0.999. Then you can be reasonably certain about the event's occurrence. Instead, suppose you believe the probability of the event is 0.1, then you can be reasonably certain about the event's non-occurrence. And finally, consider the case where the probability is 1/2. There you have maximal uncertainty about the specific event's occurrence. When we want a measure of uncertainty that is not referring to a single event, in other words, not referring to a single probability, but a set of probabilities, then we turn to the notion of entropy. Suppose you have a variable x, which takes values from a set of events. Each event is labeled as xi, where I is the index of the event. Then we can obtain a measure of uncertainty of the set of events by this expression, which is the famous Shannon formula for the entropy of a random variable, which is the negative sum of the probability of every event multiplied by the logarithm of that probability, under the constraint, of course, that the sum of the probabilities must come up to 1, because each of the events is a partition of the space of the events, and therefore the sum of the probabilities of the events in the partition must equal to 1. So this is taken directly out of Shannon's work. This is a graph. On the y-axis, we have entropy in bits. On the x-axis, we have the probability p, which of course goes between 0 and 1, of a 2-event distribution, where the probability of the first event is p, and therefore the probability of the other event must be 1 minus p, given the constraint that we just mentioned. As you can see, entropy has its maximum, or the uncertainty is at its maximum at a p-value of 1/2. In other words, when we have a probability distribution of 2 equiprobable events, when the events are equiprobable, this is maximal uncertainty, and the value of entropy is at its maximum. On the other hand, if the probability is 1 or 0, or if the probability p of the event is 1 or 0, then there is no such uncertainty. The probability is 1, you have certainty. The probability of 0, when p equals 0, then the complementary event is certain. So once again, there is no uncertainty. So the minima are found at probability 1 or at probability 0. The second and final notion I will need is the notion of surprise. And surprise refers to a particular event and quantifies the information which is conveyed by that event. So it's the negative logarithm of its probability. Let us make sure we can contrast this now to entropy, which measures the expected or the average surprise over all events. So this is the expression for our entropy. We can slide the minus in because this is just a sum of terms. Then we notice that these two terms are the same. So we can replace the term there by what's on the left-hand side in the top expression. And so we have that this expression, which is the sum of the probability multiplied by the surprise of the event, which is of course equivalent to the mathematical notion of the expected value or the mean of surprise across all the events. Okay, we're ready, even with such minimal technical apparatus, so to speak, we're ready to see if we can make any sense of what's happening in the habituation switch paradigm. So we have stimuli. As I said, there is stimuli of 2 types. There is visual stimuli and there is acoustic stimuli. And by combining stimuli, we can make up events. An event is a pair of a visual stimulus paired with an acoustic stimulus. So we have 2 visual stimuli, 2 acoustic stimuli. Therefore, we have 4 possible combinations. We have 4 possible pairs. Before the experiment begins, these events are equiprobable, meaning that the infant has no way of knowing, if you chose your stimuli right, the infant has no way of knowing which of the acoustic stimuli will be paired with the visual stimuli, and therefore we can compute the entropy. We have 4 events, they are equiprobable, and the entropy turns out to be 2 bits, and that makes sense. We have 4 possibilities, you need 2 bits to encode 4 possibilities. What happens during training? Via training, we have 4 possibilities, which actually become 2, because arbitrarily here, I'm choosing to present only event 1 and event 4. Remember, during the habituation phase, we're only presenting 2 pairs of a visual stimulus with an acoustic stimulus, not 4, 2. So therefore, this means that the probability mass has now shifted to 1 and 4, and the rest of the events get probability 0. So now the entropy is equal to 1. We plug in these probabilities in our expression, the entropy has reduced. Training reduces entropy. We do not have a maximally uncertain situation of 4 equiprobable events. We're only presenting 2 of the events. So it makes sense that the entropy has actually been reduced. And it makes sense that the entropy is also equal to 1, or the uncertainty equal to 1 bit, because we have 2 events. And in order to encode 2 events, you just need 1 bit. Of course, the probabilities are not directly available to the infant. They must be found on the basis of experience. So the infant must do some sort of estimation of the probabilities on the basis of experience. I will assume here that the infant estimates the event's probability distribution via Bayesian learning. So in particular, we can estimate the probability of event J at time step I, time step during the training phase, during the habituation phase, by the mean of a Dirichlet probability distribution whose parameters are updated using Bayesian learning. I'm not showing you how we do that. I'm just showing you the results of the simulation. So on the top, we see the evolution of entropy as a function of trial number. So on the x-axis, we have trial number, and on the y-axis, we have entropy. So entropy begins high, because we have at the beginning of the habituation phase 4 equiprobable events, and progressively, because only 2 of the events are being presented, entropy reduces, as we've seen in the previous slide, to a lower value. So as you can see, entropy progressively falls as the trials accumulate. And in the lower panel, there we're showing as a function of trial number, surprise, where surprise again, remember, refers to a particular event. And of course, surprise fluctuates up and down, depending on which of the event is being presented. At the end, we plot the surprise of the same versus the switch trial. And of course, we can expect that the surprise of the same trial, this is the trial that has been presented half of the time during the habituation phase, because we're only presenting 2 pairs. So one of the same trials in the test phase has been presented half of the time during the habituation phase, but the switch trial has never been presented in the habituation phase. It's one of the combinations of the acoustic and the visual stimuli that we never actually presented. And therefore, as a result of this, we expect the surprise of the same trial to be less, relatively speaking, than that of the switch trial. And this is precisely what we find in the experimental results. So in other words, in the switch trial, we find greater looking times for the switch trial as opposed to the same trial. So things make sense so far. I'd like now to see if we can take this a bit farther and ask the question, how does the infant find the phonetic cues of the stimuli they should attend to? In particular, consider hearing an acoustic stimulus and aiming to predict what the object was on the basis of this stimulus. Here, we're going to be using the conditional entropy. In other words, how much uncertainty remains about the object being named given the cue. Given knowledge of the cue, how much uncertainty do I have about which object is being named? And incidentally, what I'm going to show you here is not new. So we are proposing here a standard, what is already standard in decision tree construction these days, or about 5 years before it was called machine learning. So let's suppose then we have multiple speakers, as in one of the standard run, what I call the standard run of the habituation switch paradigm. Each of the speakers is saying book and book. And what I'm displaying here is contingency tables of our phonetic cue values. Suppose we only entertain 2 phonetic cue values, VOT and F0. So these are contingency tables of the phonetic cue values and the visual stimuli A and B. So in particular, this value right here is telling us that the probability of seeing the visual object A and hearing a low VOT value is 0.9. This makes sense because we chose the pairing object A with the voiced B. And this probability is telling us that the probability of seeing the object B, so now the object B is paired with a voiceless, and therefore in any Germanic language, English or German, then we expect to have hearing a high VOT, then the probability of that plus object B is 0.9. And of course, acoustic stimuli can also be classified in terms of F0. And here I chose 4 subcategories of F0. I could have chosen 2, 3, or 4. It does not matter as far as my demonstration is concerned. So we have the F0 value and the probability of object B or object A of A or B given that F0 value here. So in particular, this is a male speaker with a rather low VOT, and the last one is a female speaker with a rather high VOT. So what we seek now is a formal expression of what is, I think, patently clear in this table. So in other words, that knowing VOT goes a long way in reducing the uncertainty of which object is being named, but knowing F0 does nothing to resolve that uncertainty. For that, we need to compute the conditional entropies, as I said. So let's compute the conditional entropy of the object given the low value of VOT. This rests on the distribution of the probabilities here. This is a highly asymmetric distribution. These are not equiprobable events. And therefore, the entropy of that is expected to be less than 1. And indeed, this is what the value is. The same thing for the conditional entropy of object given a high value of VOT. We get the same value, of course. And then moving on to the F0, this is the conditional entropy of the uncertainty of which object is being presented given a very low value of VOT. Here we have we have 2 possibilities. Each of the possibilities gets a probability of 1/2. So we have a symmetric distribution, which is, of course, it's going to give us the maximum of entropy, which is 1. So the maximum of uncertainty, and the same happens for the other values. So the answer to the question, which Q helps the infant succeed in this task, can be expressed by this notion of maximization of information flow. The information flow is given by the difference between the original and conditional uncertainty when you're agnostic about phonetic cues, when you know no cues, minus, this is the reduction in uncertainty you get when you take into account one of your cues. This is the uncertainty given the cue. So if we use a VOT in order to express information flow for the cue of VOT, we know that the entropy will reduce by this value, which we found by the previous tables, and therefore we get a reduction in the original uncertainty if we use VOT. On the other hand, if we use F0, because the uncertainty for F0 remains equal to the original uncertainty of 1, we're not maximizing. In fact, the quantity becomes 0. So in contrast to VOT, F0 does nothing to reduce the uncertainty about which object is being named. So this is one way we can express formally that VOT is a relevant cue in this paradigm, whereas F0, it's not a relevant cue. So things seem to be working. So let us then try to push this a little bit farther. So I'm going to look now beyond Q relevancy. And in particular, this is the point where, as I said, we will try to synthesize the Q-based and the task-based account for what's happening in the habituation switch paradigm. So in other words, we're going to try to account for looking times, because this is really what we care with respect to using that paradigm in language acquisition research. In order to demonstrate how we can do that, I will use this intuitive idea that has been pursued in some of the experimental work using the habituation switch paradigm. And that idea is based on what seems entirely reasonable, which is that when you highlight the phonetic differences between the 2 words that you intend the infants to learn, then you expect to facilitate it. Then you expect finding a switch effect, or you expect to make it easier to find a switch effect. But this is not always obtained. So for example, in this rather interesting study, Kwam, Knight, and Gherkin had infants hearing only women saying pook or only men say book. Of course, they had a counterbalanced condition where things were exchanged. And training under this condition, which was referred to as the correlated gender condition, was compared to a condition where both women and men utter both words. I'm going to call this the standard run, when both genders utter both words. The result was that looking times increased in the correlated gender condition compared to the uncorrelated gender condition. And a plausible interpretation of this is that, I seem to have skipped the figure demonstrating that. So this is the standard run, what's shown here, where we do get a switch effect. here are the looking times for the gender correlated run, and you can see the looking times shooting up to 10.5 seconds, which is a rather long time for word learning paradigms using the habituation switch task. So there was no switch effect. A plausible interpretation of the failure to get a switch effect is that the task is complex. So a plausible interpretation is that longer looking time in the same trials may reflect the greater complexity of the task. This notion of complexity of the learning situation now receives a natural expression in our approach. The key idea is the following. The information contained in a stimulus is a function of the contingencies which are established in the habituation phase. The different habituation phases establish different contingencies about which cues covary or do not covary with respect to other cues. And these contingencies, in turn, generate a task-dependent space of contrast relations among stimuli. Information is all about this contrast space, is about the set of alternatives. This is the notion I promised to be highlighting throughout the talk. In particular, we have 3 dimensions in the correlated gender situation. We have a visual dimension, which takes 2 values, object A, B, and gender dimension, 2 values, and a voicing dimension, also 2 values. Therefore, we can represent the stimuli by the vertices of the cube, because we have 3 dimensions. In each of the dimensions, you get 2 choices. We have 8 possibilities. And there is a particular structure to this situation. So, for example, when we say stimulus AF plus V, we mean a stimulus which displays the visual object A, spoken by a female, saying the voice stop V. And in particular, when we look at the structure of the cube, so the front face of the cube right here is all stimuli which are spoken by a female. So you can see the features here, F, 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 for all the vertices in the front face of the cube. In the opposite face of the cube are all the stimuli spoken by a male. In the right side of the cube, it's all the stimuli that display the visual object B. In the left side of the cube, all the stimuli that display the visual object A. And finally, the bottom, all minus voice stimuli, and the top, or all plus voiced stimuli. So let us then compare now the standard and the gender correlated run. In the standard run, we do not have the gender cue playing a role. And in particular, consider the information status of an event, which is A, coincidentally spoken by a female. So the circled event, let's assume it's coincidentally spoken by a female in the standard run of the paradigm, who produces A plus V. That stimulus has quite different informational status from the physically identical stimulus presented in the situation of the gender correlated run, in a situation where we have 3 dimensions as opposed to 2 dimensions. Why does it have rather different informational status? Because the 2 stimuli are embedded in a different set of alternatives. This is a rather counterintuitive and fundamental aspect of Shannon's theory. This is the role of the probability in defining information. In other words, information is not a function of what the stimulus is, but rather of what it might have been, of its set of alternatives. So the dimensionality of the space that I displayed, so the dimensionality of the space of alternatives, is directly related to the notion of entropy. In particular, the higher the dimensionality of the space, the more the alternatives, the higher the entropy. This in turn allows us to make looking time predictions on the basis of the structure of these contrast relations. There's a basic law in response times to perceptiomotor choice, which is that the time to make a decision or respond to a stimulus is a function of the information contained in the stimulus. This is the expression of the Hick-Hyman law. And as you can see, H is part of that regression equation. So H is the information entropy of the task, and A, B are empirically determined regression coefficients. So we can now begin to derive looking time relations across the different runs of the habituation switch paradigm. In the standard run, the dimensionality of the task is 2. In the general correlated run, the dimensionality of the task is 3. The entropy for 2 dimensions is less than the entropy for 3, hence the increase in the looking times. We can fit a population level estimate into our data as well as data from previous studies using the habituation switch paradigm, which gives us this expression where N is the dimensionality of the space of alternatives and K is a negligible constant, which seems to depend on the particular population. So I'm ready to sum up with part one. What we have seen is that in the habituation suites paradigm, infants construct a model of the source, they estimate the probability distribution of the events. Surprise, in an information theoretic sense, modulates looking times to same versus suites trials. And entropy of the training phase also modulates looking times. Both of these results are shown here qualitatively. I'm now going to turn to the part two, which is rule learning. And in particular here, this part will be quantitative. So there will be numbers. So what I would like to do in this part is that I would like to extend the application of the key notion I am proposing in this talk, the key notion of choices among alternatives. I would like to propose an application of this idea, or to extend the application of this idea to the artificial grammar learning paradigm. This is a paradigm, and in particular to the artificial phonology subfield of that paradigm. So here we have an experimenter who aims to teach participants sound patterns that sometimes reflect and sometimes do not reflect phonological systematicities attested in natural languages. For example, take rule one. In rule one, this is a made up sound pattern where stems that are trisyllabic end either in the suffix na or in the suffix la. And of course, when we set up a rule, when the experimenter sets up a rule, it's what is the conditioning environment for the presence of na. So na is attached to stems that end in nasals, M and N. Otherwise, if the stem does not end in a nasal, for example, KG or TB, whatever, then the suffix is la. And this rule, so in a 20-minute session, this rule was taught to English participants, and in a different, of course, session, a random rule was taught. So I should say that rule one is attested. It is an assimilation rule. Rule two is not attested. Rule two is a random rule where the suffix now is na only if the stem ends in kg. Otherwise, the suffix is la. I'm taking these examples of two rules from a paper by Colin Wilson in 2003 that produces this rather nice demonstration that the outcome is that rule one, which is you attach the stem na if the stems end in mn, is learned, but rule two, if the stem ends in kg, is not learned. I should say, more appropriately, we should say is not learned as well, but this is how things are presented. So rule one is learned. Rule two, the random rule that's not found in any language, is not learned. The basis of such results has so far remained unclear. Very nice reviews have appeared in the AGL paradigm, in particular in the artificial phonology field recently that are cited here. So the question is the asymmetry due to learning, which is guided by grammar-specific evolution? For example, perhaps there is an encoded version of what is a natural rule. These are other word for this is inductive biases that drive the learner to prefer to certain generalizations and not others. Or is the asymmetry in learning due to an asymmetry in information flow between the source and the learner, the same notion I presented in the first part? In particular, I think there's three mysteries here. Why do such asymmetries exist? What's the basis? What generalizations are formed by AGL learners, and how fast do learners form this generalization? And my aim here would be to demystify the why part. So we can begin to do so by asking the following question. How well does the acoustics specify phonemes? In particular, remember the MN rule. This was a rule where the suffix was conditioned on the presence of an MN in the stem. Hearing nasalization specifies exactly the class of phonemes, MN. So in other words, an alternative to say this is that hearing nasalization reduces the alternatives on the perceiver side just to the class MN. On the other hand, hearing a stop closure specifies at first a broader class of segments, namely all the stops. Further processing is necessary to home in into the subset KG. Stevens and Kaiser, as well as Ohala, have proposed empirically based distinctions between robust and weak features, with nasality being a robust feature and place of articulation being a weak feature. To gain a qualitative handle, however, let's move on to the go-to source for how well acoustics specifies sets of consonants. And that's the seminal study by Miller and Ainsley in '55, in the Journal of the Acoustical Society of America, where they produce confusion matrices for 16 English consonants under 6 different SNR conditions. Each of the matrices contains 4,000 data points for a total of 24,000 data points. This is what a confusion matrix looks like. In each row of this table right here, I don't intend the audience to be able to read the tiny numbers here, just to look at the structure of the table. Each of the rows in this table is one of 16 consonants they presented to the listeners, next to a vowel, of course. And each of the columns here is the same 16 consonants. And in particular, in each of the cells, we find the frequency with which this consonant followed by a vowel was responded to as that consonant followed by a vowel. So in particular, consider, for example, what the responses to K were. K was responded to with K 62 times and with G 1 time. G was responded to with K 1 time and with G 29 times is that number. But compare that to M and N. M was responded to with M 109 times, and N was responded to with N 145 times. In particular, if you look at the structure of alternatives in the responses, we see that K was responded to with other consonants quite often. In other words, if you look at the density of the responses to K, other consonants came up as responses to K quite frequently. The same thing happened with G. You can see the numbers here are quite large compared to the numbers I'm going to show you for M and N, and the same thing with the same thing with G. The alternatives to G, so in other words, G was responded to with non-G responses with quite high frequency compared to what we see here for M and N, where you can see that the rows now are rather sparse and the frequencies are lower compared to those of KG. Once again, the key notion appears. The set of alternatives for KG is more populated and their frequencies are higher compared to M and N. So the question, which class of consonants do listeners note best or most reliably map to the intended set of consonants, can be rephrased as one of which of the two classes, MN or KG, has higher information flow between the source and the listener, between what the experimenter was intending to provide to the listener and what the listener actually perceived. This is the same quantity as we used for infants for the part 1 of the talk. It's just expressed in a different formal way. These two equations are formally equivalent. This is the entropy of the stimulus, that's the entropy of the response, and that's the joint entropy. The higher the information transfer, the more information has flowed from the source to the listener. This is what we're after now. So we can reduce now each of the tables from the Miller and Nicely study to a smaller table that consists that is specific to the rule MN. This is the top left one. So in particular, in this table, this is MN versus other category. Was the stimulus MN or was it other? And the responses, was the response MN or was it other? We can determine probabilities. We can do that because we have 4,000 data points, so we can go from frequencies to probabilities. We can compute the entropy of the stimulus, which is based on, of course, on the marginal probabilities of the stimulus. The entropy of the response, which is based on the marginal probabilities response, and the conditional entropy, which because it's the conditional entropy, and joint entropy, which is based, of course, on 4 probabilities because we have a 2x2 matrix. And this is giving us the information flow for the particular signal to noise ratio represented by this table, which gives us some value of information flow for this signal to noise ratio. And we can do the same for KG as well. So now we're ready to plot our results. This is the information flow shown on the right and a relative version of the same measure, a dimensionless percentage where we divide the information flow by the original entropy of the distribution. And this value is the value that I showed you how to compute in the previous slide. Okay, so this is one value that we picked at an SNR of minus 12 decibels. Of course, Miller and Nicely did it for 6 different SNRs. 6 different SNRs are shown here for the 6 values. What is clear is that the input class MN, which is the blue line or the line on top, is more strongly associated to the output class MN than the input class KG is associated to the output class KG throughout the entire range of SNRs. Again, these figures are based on 24,000 data points. In other words, the information the learner has about the input is less in the case of the KG compared to the MN rule. There is thus a very clear asymmetry in information flow between the assimilation rule and the random rule, which does not require any recourse to inductive biases. So with respect to the question that we raised at the outset, in other words, what is the basis of such results in the artificial grammar learning paradigm, we can state two things. First of all, rules must be learnable by the child, in other words, adapted to the cognitive skills of the individual. Second, the patterns that are encoded in rules must be transmittable or reproducible. In principle, both of the rules, both the assimilation rule and the random rule, are equally learnable by the individual if you give them sufficient input. But the former rule is not reproducible, is not as reproducible as the latter rule. So I'm ready to sum up part 2. So what may be a plausible basis for the asymmetries in artificial phonological rule learning? One, quantifiable basis. It's important that it's quantifiable. So far, we have not had a quantifiable basis in these experiments. One quantifiable basis is information flow. There are likely, of course, to be other bases for the complexity of a rule. And the moral is that the transmittability of a sound pattern, X versus Y, here, for example, how well the intended sets M and N or KG reduce the choices among alternatives at the side of the perceiver. The reproducibility of that pattern reflects whether these sound patterns are likely to be attested in languages. I'm ready now to move to part 3 of the talk, which is the distinction or the plausibility of drawing a distinction between speech versus non-speech. And I will be presenting some new results based on phase space reconstruction of speech movements. This part will be topological. This part will be dynamical, geometric, or topological. So this is the question that appears in the very first page of the Sapir article that I started my presentation with. So Sapir said that the best way to appreciate the psychology of speech sounds, what he called the psychology of speech sounds, what we can rephrase as what is exactly linguistic about speech sounds as opposed to other sounds, is to compare an actual sound with an identical or similar sound not used in a linguistic context. So what is a good candidate for doing that? We think the answer is wind instrument playing. Wind instrument playing involves repetitive attacks with one part of the tongue, either the tip or the tongue body. And these are called single tonguing and double tonguing. Trainees are explicitly told to form speech-like T and K gestures. Hence, speech-like movements are definitely implicated. And furthermore, keeping on tempo is absolutely crucial to trainees. This is what they do. They do training under different rate conditions of repetitive attacks called single tonguing or double tonguing. Here is an illustration of a trumpeter doing double tonguing. We have a sensor that's placed on the tongue body, and the movement is recorded using our electromagnetometer system. And we have another sensor placed on the tongue tip, and the trumpeter is performing at 150 BPM, which is a relatively slow rate, repetitive attacks, either with the tongue body or with a tongue tip, so forming effectively what would be a speech-like K gesture or a speech-like T gesture. Here is a sensor animation of the speech taka now. So this is the same speaker, the same individual as before, producing alternate attacks of T and K, but now in the speech mode. He does not have a trumpet in his mouth. He's just speaking taka at a very large number of rates. We find what you expect. So upward raising of the tongue button sensor for the K, upward raising of the tongue tip sensor for the T. In thinking about this data, I will need the notion of phase space. So the phase space for two-dimensional systems, so these are the systems that the field of human movement science assumes underlie movement, biological movement. So we have 2 dimensions, it's position and velocity. So suppose, for example, you start from 0 velocity, you pick up velocity, and then you hit your target right here at the value of 0, let's say 0,0. Or you may start from a position that's higher than your target position. So your target position is at the origin is at the origin of the coordinate space. And here we started from a higher position. We pick up velocity. The velocity is negative because we're going down. And then we hit our target eventually. So this is the phase space of the dynamical system underlying discrete events. And I need this phase space because it's going to play a crucial role in the distinction between speech and non-speech. So if we use the computer to display what the phase space looks like for all possible positions, we get the flow of the dynamical system, again, in the two-dimensional space of position and velocity. And the trajectory shown there is how the parameters of position and velocity evolve for any original position in the phase space. So in particular, what's going to be crucial is this distinction between time series and phase space. What I'm showing on the top is the time series. So in other words, the evolution of a position as a function of time on the x-axis, and the evolution of velocity as a function of time. And this is the first derivative of the position. So these are time series data. And on the bottom, and this is the harmonic oscillator. This is a familiar system. On the bottom is the same system I showed earlier. This is the system that is thought to underlie any discrete movement of an effector, be it a movement of the eye or a movement of the finger or a movement of the tongue. So the top system is the harmonic oscillator. The bottom system is the dynamical system thought to control any discrete movement. In the phase plane, the trajectories that correspond to these time solutions for the harmonic oscillator will look like loops. They will have this particular geometric shape. In the phase plane, the trajectories that correspond to the time solutions of the discrete movement system will look like these hooks that we saw in the previous slide. So you can think of the dynamics as imposing a specific geometric structure in phase space. This third part of the talk will be about geometry and topology, as promised. And in fact, in the dynamics, this is where life happens. In dynamics is not where you start and end your movement, but the way you travel through the phase space. That is what captures the dynamics of the underlying system thought to control movement. So I'm going to be relying very heavily on the aspect. We'll be looking for dynamical signatures or regimes, which correspond to entire equivalence classes of movement patterns based on their topology. And two different regimes, two equivalence classes of movements are mathematically incommensurate. This is a theoretical result. This is not an empirical result. In other words, one cannot be reduced to the other due to two fundamental theorems from dynamical systems theory, the Poincaré-de Dixon theorem and the Hartman-Grobman theorems. So prior work seeks differences between speech and other orofacial activity in relations among kinematic parameter values. That's not a topological perspective. This is trying to find distinctions in kinematic parameter values. Here is a set of relations that's known to hold for speech. These relations express invariances among peak velocity. It's this parameter right here, V star, amplitude, A, time, T, acceleration or peak acceleration, and curvature. These are vital to appreciating. So these relations are vital to appreciating the abstractness of the principles that govern speech, but they're equivocal with respect to the underlying dynamics. It is a different talk to explain why they're equivocal with respect to the underlying dynamics, but let me say one rather intuitive reason. Notice that each of these relations chooses a certain set of parameters. So for example, this relation chooses just 3 kinematic parameters. We start with a continuous spatiotemporal structure, but here we're reducing it to the relation between 3 parameters. So there is highly selective. These relations are highly selective. Nevertheless, they beautifully hold across the entire range of variability of these parameter values. So they're rather vital to appreciating the abstractness of the principles that govern speech, because they are effector invariant, for example, and they hold throughout the parameter range. But unfortunately, they don't tell us anything about the underlying dynamics. Nevertheless, let us look at what the results look like for speech and trumpet data. So what I'm displaying here, I will only talk about one of these relations. This is the famous 1/t relation. We have movement duration on the x-axis, and on the y-axis, peak velocity divided by amplitude. as the movement duration of a discrete movement decreases, so as I ask you to perform the movement in a shorter time interval, the peak velocity over amplitude ratio will increase, okay? Either, of course, by increasing peak velocity or by reducing amplitude. What in phonetics is being referred to usually as phonetic reduction, okay? As the movement duration shortens, peak velocity over amplitude shoots up. In any case, there is no qualitative distinction between the two settings. Speech and trumpet taka exhibit the same kinematic relations. So I mentioned that these relations are equivocal with respect to the dynamics, in part because what I will show next is that underneath this similarity between trumpet and speech taka, there are qualitative distinctions which are hidden and we can only see if we look in the phase space topology. So we're ready now to look into the phase space topology. Let's look at the trumpet data right here. This is the phase space topology for 150. This is the phase plane, this position here on the x-axis, and velocity on the y-axis. And what's here is the time series. Here is the phase plane representation, and here is the time series. The bottom panel is trumpet, the top panel is speech. As you can see, when you consider the full spatiotemporal properties of the movements in phase space, the trajectories in phase space are different. And in particular, they are topologically non-equivalent. So these two trajectories are topologically non-equivalent trajectories in phase space. This notion of non-equivalence rests on formal results from the field of topology. In other words, there exists no homeomorphic transformation which could map the trajectories in speech taka to trajectories in trumpet taka. This is a qualitative distinction. We're not looking at parameter value ranges, we're looking at qualitative distinctions. And the crucial result for us is that topologically non-equivalent structures imply qualitatively different control regimes. Using the dynamical topological perspective, we are able to demonstrate that even with extremely similar speech movements, so physical movements, speech can separate from very similar activity, that is, for example, here, trumpet playing. However, at 480 BPM, so this is extremely fast, okay, 250, 220 is, and BPM is normal speaking rate, 480 is extremely fast. Speech and trumpet taka now converts to the same topologically equivalent single periodic pattern. So here is what happens across the different rates, and I will summarize. At rates below 300, speech and trumpet trajectories are topologically non-equivalent. This is a qualitative result. Topologically non-equivalent trajectories imply qualitatively different control regimes. But at rates above 300 BPM, speech and trumpet taka converts to the same topologically equivalent single pattern. So we can separate speech from non-speech, but what happens in speech as you scale rate? This is the final part of the third part where I will be presenting phase-space reconstructions for speech data. At issue is when you speak rate, when you speak in the speech mode and you produce repeated syllables, what is the nature of the underlying dynamics, which means what is the number and the type of attractors we find there. So a repeated Cas sequence, let's take the example of a Cas sequence, is expected to involve two gestures. Okay, so we as linguists and as phoneticians, we expect to find a gesture for the vocal tract configuration required for K, which is a constriction affected at the tongue palate contact, so a maximal degree of closing and a maximal degree of non-closing of non-closing or of opening for the vowel A. In terms of the dynamics, then we expect two fixed points at opposing extremes of displacement. The classic dynamical approaches to speech and other biological action assume a second-order dynamical system that's shown here. The nature of the function f is, of course, under debate, but all models agree about the presence of a fixed point in the dynamics. This is what endows the system with the wonderful property of equifinality. So in other words, regardless of the initial condition, you can convert the characteristic state that the linguist assumes corresponds to a phoneme or corresponds to a gesture. A phoneme is a set of gestures, so there's definitely one gesture there. So in particular, let's use the example of task dynamics. So the fixed point here in task dynamics is represented by this value f0. This is the fixed point or the point attractor in task space. So let's look for them. Theory and linguists predict the presence of fixed points in repeated K sequences. Let's see if we can in fact find them if we look at phase space. So stable equilibria, so first of all, how would they look like? How would this equilibria look like in phase space? We need to understand what the fixed points look like in phase space. And fixed points in phase space are spatial states of the phase space. Remember, the phase space is the space of these two parameters, velocity and position. They are spatial states in that they suck in or they pull in nearby passing phase trajectories. In other words, the attractors accumulate probability mass in the phase space. So we need to be looking at the phase space probability density. Now, in fact, if we read dynamical system theory on the point, it says that for two-dimensional systems, you should actually be expecting two types of attractors, not just fixed points. This is what linguistic theory posits, which are localized point-like regions of high density. But you should also be expecting periodic attractors, which are closed ring-like structures of high density. This is the results of the phase space reconstruction over data. Each of the rows of this figure represents a speaker. So the speaker on top, a different speaker in the second row, and so on and so forth. And each of the columns represents a speech rate, 150 BPM to 570 BPM, extremely slow to extremely fast speech. What you can see, in particular, let's say we pick this speaker right here, we see that we find fixed point attractors, which are localized point-like regions of high density. This is where we expect the attractor for K. This is the extreme degree of constriction. This is the maximal degree of constriction because the x-axis is displacement or position. So this is where we expect to find a fixed point for K. And this is where we expect to find a fixed point for the vowel. And that's exactly where we find them. We find the presence of the attractors exactly where we expect them. However, a rate higher, the same speaker shows only one attractor, only one fixed point for K. The attractor for the vowel has now dissolved. And moreover, yet another speaker, for example, this speaker right here, shows no evidence for fixed points, but rather evidence for the theoretically predicted limit cycle, for the theoretically predicted periodic attractor. Periodic attractors are these closed ring-like structures of high density. So what appears on the surface then, when you invite your participants to the task, and the participants are told to repeat syllables as in ta-ta or ka-ka, what appears on the surface is a monotony of reiter and kas. What lies beneath is this new result, that there is no fixed isomorphism between the spoken utterance and its underlying dynamical organization. It's easy to take a sort of a bird's eye view on the data, lump across the different speakers to see what's actually happening qualitatively. So we find one sequence, one repeated syllable, distinct dynamical organizations. At slow rates, we find 2-point attractors, one where for K, the other for A, exactly where we expect them to be, exactly where linguistic theory expects them to be. At modest rates, only one attractor, for the K, the A attractor has disappeared at the maximal opening here. And finally, at fast rates, we find a limit cycle. We find a periodic attractor, which is theoretically predicted. Okay, so close to summarizing, the dynamics we have so far investigated can be interpreted in informational terms, in terms of the choices that speakers exhibit about the presence or the absence of attractors or of a target and its degree of accuracy. And here we meet perhaps the most well-known law in human movement science, which is Fitts' law, which has an explicit information theoretic interpretation. I will not elaborate on this, but we have expanded on this informational theoretic interpretation in a published paper. I chose not to speak about this because the results are already published. Ready to sum up part 3 and the talk. We have seen that the topological perspective provides a basis for a qualitative distinction in speech versus non-speech. That phase space analysis offers rigorous evidence for the concatenation of discrete speech gestures, but it also offers evidence for theoretically predicted alternative organizations, in particular, the long-sought limit cycle in speech tongue movements. Limit cycles, of course, have been argued to be found in other areas of human movement, for example, in fingers, but of course, tongues are not like arms or fingers in that they contain no rigid skeleton. And I will refer you to Eleonora Albano's talk to the extent that I will follow the talk because in a different it was in a language that I don't speak, the talk elaborated on this fact about speech movements. Thank you very much. It's the end. That's all I've got. Eleonora, I believe your audio is turned off.
Mute. Here I am. So you were an admirer of Paulo Coelho, and he worked very hard on the resistance about 30 years ago, and he's resisting. Okay, let's talk about science, because this is one way of resisting, as the series of talks has demonstrated. I have very general questions from the people who have been able to join, okay, because some have not, you know, they have to teach this. We have a different semester from yours, so things are still going on.
Sure.
We are kind of behind because of the pandemic, and then some people had to some were teaching at the beginning and are showing up now, and some are leaving because they are teaching. But I have some questions from, the first one is from a musician who is in the Dynaphone group, my research group that I lead. And he says, one issue, entropy, is an important measure for information science. Would it also be applicable to measure voice quality? Is it tenor? There are two people in this group who are singers, classical music singers. We are studying voice quality together, all of us for different reasons. So he asks, would it also be applicable to measure voice quality? Could some criteria be applied regarding the glottal closure ratio, or better, regarding laryngeal activity? This is Antonio Pessotti, who has just left because he has to teach a class, and he left us.
Yeah.
Can you give perhaps some speculative thoughts on that? Because this, I can see that the trumpet subject has been very well researched, and of course, you know, this is just hunch that came to Antonio because he is very much interested.
Yeah. I believe the notion of entropy is related to many things. And in particular, at a first level of approximation, you can consider entropy as a measure of variability of a random variable. So in this case, I suppose you have in mind voice quality or data where presumably the variability of the distribution is characterizing something about the task. And unfortunately, I cannot speak in precise terms because I do not know what is being characterized by the task.
I think he's not here to help us narrow down the question, but I think he's talking about singing registers, because, you know, there are some abrupt changes and things like that.
Indeed, yeah. So as I mean, the first level answer would be if a measure of the if the measure of the degree of variability in the distribution of your parameter values is of interest. And in particular, if the probability distribution of the different parameter values captures something about the skill or the state or the pathology of the situation, then that measure may very well be useful. So entropy and in particular information theoretic measures have a wonderful underlying assumption that is extremely general. So in particular, the topological structure of your variable is irrelevant with respect to the applicability of the measure. So all I need is an assumption on the side of the specific domain as to whether the two samples that you take from your data are same or different. If this is a rather minimalist assumption about the topological structure of your variable. So once you have that assumption, and a lot of phenomena have that assumption, and that's in part the reason why the talk has applied itself to very different phenomena here. The reason for the applicability of these notions to many very different phenomena is because of the rather broad nature of that assumption. So in other words, that you can compute measures of the variability of your distribution with just the precondition of the things being same versus different. So as long as you as the researcher believe that there is something interesting to looking at the variability of the distribution itself, then entropy is of course a measure that you can use, that you can apply to your data. As I said, I lack, unfortunately, due to my ignorance, I lack specific knowledge of the domain, and so but that's, let's say, yes, I believe that this notion is in principle applicable in any phenomenon where you're interested in variability among your.
Thank you very much. I think Antonio will be delighted to come back to this video when it's on YouTube, and perhaps he can email you some questions if you don't mind. There is also the other thing, Beatriz Raposo de Medeiros. She's rather uncertain about 480 BPM. She says 480, most of the activities I know about 120, what to make of that?
Indeed. We did not collect data at 480 because we believe it's at some range of cultural expression for the instrument. Rather, we wanted to have as great a range of variability in our metronome because, in part, in prior work, only 3 rates, maximally 3 rates, have been registered in work that we have been able to track using metronome elicited biological activity related to speech, and also in part because we very much wanted to get our hands on the phase transition or on the possibility of seeing a qualitative change in the dynamics. And so indeed 480 is extremely difficult to sustain, and however we maxed out, we very much simply maxed out our range. We see the qualitative changes beyond 210, so we do see qualitative changes beyond 210 BPM. So I'm not sure if my slides are displaying anymore, but
yeah, you can go back to your slides, yeah. If you.
So if they are, then by looking at these distributions, you may be able to see that even on 210, we can see distinctions in the qualitative structure of the phase space. So for example, here, the vowel for this individual is not there at 210 BPM. And 210 BPM will be considered quite habitual, let's say, rate of speaking.
I see.
So so this is just us driving our experimental subjects crazy with collecting as much of their activity at different rates of the at different metronome rates. I agree that 570 and 480 and even 480 and maybe even 390 for some individuals are way beyond what would be considered a normal rate of activity.
Well, but there are virtuos, people who can achieve higher rates of any activity. Well, there are many messages thanking you. You are only have access to these messages later when YouTube posts the talk. But there's still one question from Thais Christoforou. Thais Christoforou was the hostess of my talk. You can remember that? And I'll have to switch to Skype because that's where she wrote it. Based on Shannon 1948, messages are understood as a sequence of choices amongst a set of alternatives. So it's making sure she understood what you said. Does this view suggest that words or constructions rather than sounds are the locus of representation? Does this have anything to do with bigger chunks?
I think the granularity issue. So yeah. In other words, how big the chunk is orthogonal to the issue of the choice. So I am as I'm thinking about the question, I suspect whether the question has an underlying deeper aim, which is whether we can squeeze out of this anything about, for example, whether the infant representations at the start are more. Okay.
That's I think what she has in mind. But she's around, so maybe she wrote. Let's see if I have something else from her, because she does have some data on language acquisition and so on. But
this is a wonderful question. So whether the extent to which so whether the size of the unit itself is discernible in any way. So I would say that from the perspective of Shannon, from the perspective of Shannon's theory, the granularity issue is orthogonal to the basis of the theory. This means that you can memorize a sequence of events. Let me just use a parochial example. You can memorize a phone number, either as a sequence of isolated digits at the lowest level of analysis, or as a sequence of groups where each group has 3 digits, let's say. So as far as the theory is concerned, there is no commitment to that. There is no commitment to the granularity of the of the size. I suspect that to the extent that there is evidence for one versus another size in language acquisition, this is treatable theoretically, but it probably derives from other considerations. So in particular, the state of development of the perceptual motor system that's used to support the speech activity at that age, and or memory issues that have to do with the plausibility of maintaining more and more words, let's say, and how that plausibility depends on the size of the chunk.
Thank you, Adamantios. And Thais says, that's it. She's here on the chat to say that.
Yeah, it took me a while to arrive at that suspicion, but I knowing about the work of the individual and thinking about the relation to the talk, I realized that this is perhaps what was actually meant, which is a very deep question about which I know very little.
Ferguson, since Charles Ferguson, we have this issue about the chunks, the units in language acquisition.
Indeed.
So, yeah. Well, and now Thais says, thank you. So I don't think I have many questions. And I'll just pose a very general one, and because I had to pay attention to so many things that I will probably have to see this video again go to a specific question. The very general thing, there's well, you have already touched on that. Would you care to make some more comments on the relationship between what you talked about and the particulation issue? Granularity is about the same. I like Student Kennedy's term, particular nature of speech nowadays. I don't know how it was in our ancestry, for instance, in our primate ancestry, as we have discussed before.
Right. So I'm not sure if my slides are still displaying, but I just so happen to be on the slide of the phase space reconstruction. Is this what you see on your screen, or?
I still see you, but don't bother.
Okay.
Just give a general answer, and we can continue later. And I can tell everybody here is a friend or a co-worker. The change in schedule has perhaps made some people have to see it later. Yeah.
Right. Let me begin from a tangent, so to speak, of one of our results. So one of our results was that when we scale up rate, so we're talking about the issue of particulation, which I assume refers to the separation of the organs for performing speech into individual units. One of our results by scaling rate was that we saw that what originally starts as a concatenation of two discrete units, of two in Michael Stuart Kennedy's expression of a concatenation of two discrete units, which is what supports the notion of particulation, and in particular the notion of discrete infinity, which is highlighted in the writings of Alexander von Humboldt, but also Chomsky. So the idea in, for example, in Chomsky 2000, so the idea that we can, from a finite combination of, let's call it in our case, consonants and vowels, you can create an infinity of combinations of these units. So this notion of discrete infinity. In the phase-space reconstruction data, of course, we have verified that the discrete units are there within a certain range of rates. Beyond a certain rate, what actually happens is something that I consider to be rather remarkable, something that is predicted by theory, but has not been verified before rigorously with data, which is that the movement, the alternating movement from consonant to the vowel, which is a concatenation of discrete units, changes to a cycle. So now consider, so let me back off a little bit. So there's two ways actually to say a CV. There's two ways to combine a consonant and a vowel. One is you construct the dynamical regime where you have as many instructions as you have gestures. So you go from K to A, then there's another repetition, then from A to K, and from K to A, and so on and so forth. Notice that in this organization, in this qualitative organization, there's as many instructions as there are phonemes or corresponding gestures. An alternative way to produce a CV is not to concatenate, but to cycle through. So in other words, now the template is not go from K to A and from A to K and so on and so forth, but the template is cycle through. Notice now that the length of this organization, so the length of the limit cycle organization, or the length of what it takes for us to specify the organization, is independent from the number of units in that organization.
Yeah.
So in other words,
I get it.
All I'm saying is cycle through T and A. Okay, so but in the other organization, if I cycle 3 times, I have to specify that 3 times, or actually 6 times, because T, A, T, A, T, A. So in the final organization, notice that there is a sense in which we lose compositionality. We have lost the compositional way of putting together a consonant and a vowel. We're not composing, we're not concatenating discrete gestures anymore. So there is a sense in which we can access the loss of compositionality, the loss of discrete infinity, or the loss of the basic compositional mechanism that gives rise to discrete infinity, or I should say supports discrete infinity, by scaling up rate. So we see that the motor system effectively is pre-programmed to operate in 2 modes, the discrete concatenation mode and the limit cycle mode. I suppose that somebody who has thought about these issues from the side of the genesis of that ability may have ideas about what came first. So in particular, I believe that this is aligned with the previous question that limit cycles are primitive. Limit cycles are the fundamental primal form from which discrete infinity has emerged. So that's one potential interpretation that can be given to this. And our data demonstrates that beyond a certain rate of speech, we can actually access that organization, which is theoretically predicted, assuming dynamical systems theory, but has only been hinted at in the past, has not been actually rigorously demonstrated. Now, related to this observation, there is something that I believe it's also notable about the results, which is that different speakers, when they come to the experiment of repeating a CV syllable, when we look at the phase-space reconstruction, they seem to interpret the pragmatics of the task differently. So some speakers interpret the task as a concatenation of discrete K and R. There is other speakers, for example, I'm not sure, it's too much to ask for memory of the audience to last that long, but if you look in the panels of the phase space density, some speakers, even at 210 BPM, which is a normal speech rate, interpreted the task as not being a concatenation of K and R, but rather K release, K release, K release. There was no fixed point for the vowel. So this is telling us that we don't quite understand how deeply phonologically encoded the vocal track is when we bring participants to our experiments. So some participants interpret the task, interpret the pragmatics of the task as saying, okay, I just need to do a K closure, release it, and come back to it. I do not need to assume a vowel. Why? Because the vowel was always A. In other words, in this particular task, they realized that they could just repeat the utterance K and A without assigning a fixed point to the vowel. So different participants assign different phonological interpretations to the instructions of performing the task. And this is one of the results of the plurality of interpretations of this, which seems to depend on how the participants pragmatically interpret the task that you ask them to do. And the other is that beyond a certain rate, they all lose compositionality. So beyond a certain rate, they all converge to the limit cycle. So that there has to be something primitive about that. So why is it that beyond a certain rate, they all converge to the, I don't want to call it unmarked because that's not the organization that supports speech, but this is where they converge to beyond a certain rate.
Thank you, Adamantios. For me, at least, this was a very satisfying answer, and I'm going to think more about that. There's a message from Thais. She says she's leaving to teach. She's now retired, but she teaches English to people in the slums through the internet, as a means of resisting. So she had a class now with one of those children. It's children and adolescents in Beatriz, soprano in our group. Is she says, Eleonora, tell him I'm going to change my view about K. Gene now and teach differently to my students, teach it differently to my students. Okay. And many people say, thank you, Professor Gafos. Thank you, Professor Gafos. So I think it's time for us to close. We still have time if you want to elaborate more on this talk, because our limit is 10 o'clock. We started at 8. We still have about 20 minutes. But I think I should make use of some of this time to thank you and to thank the audience that came here so early, and also to thank Abralim for this enormous opportunity for people all over the world. I don't know how many people were here today, but I'm sure your video will grow in terms of access as soon as it's on the internet or from YouTube. So I would just like to remind the audience that they should support Abralim and that they should support all the organizations that are leading now our resistance movements through the internet. Thank you for being here. And now I ask Adamantios to give us the goodbye words, but you can elaborate on that as much as you want, because we still have time.
I don't want to elaborate on. I think I took enough time already, and I believe that I'd be more than happy to communicate and answer questions or exchange with your students and colleagues there. And once again, thank you very much. Stay healthy. And as I said, your series is, I hope, serves as an inspiration to many that are facing unprecedented challenges these days, and perhaps demonstrates a way of how we can move forward regardless the challenges that we're facing. So thank you again.